So today, let's talk about something that sounds super basic but is actually at the heart of every single microchip out there. What really happens when you touch a piece of metal to a semiconductor? It seems simple, right? But that one connection can act in two completely different ways. And understanding that difference, well, that's the key to pretty much all of modern electronics.
It really all boils down to this one simple but absolutely vital engineering question. You've got all these transistors, all these logic gates inside a chip. They have to talk to the rest of the circuit. So how do we physically make that connection happen? You'd think, hey, just lay a metal wire on top and call it a day. Easy.
Okay, so to really get what's going on, let's start by imagining a perfect, ideal world. We're going to build a flawless model of this junction. And what we're about to find? It's probably not what you'd expect. So before they even touch, we've got our two separate players. On the left, we've got a metal, and on the right, an N-type semiconductor, which has basically been tweaked to have a bunch of extra free electrons. As you can see from these diagrams, they each have their own unique energy landscape. All right, the first key idea you need to know is something called the metal's work function. You can think of it as a measure of how tightly the metal holds onto its electrons. If it has a high work function, it takes a whole lot of energy to pull an electron away. It's a fundamental property of that metal, just like its color or its melting point. Now, the semiconductor has a kind of similar property, and it's called electron affinity. This measures the energy jump from a free-floating electron down into what's called the conduction band. And that band is like the superhighway where electrons can zip around freely inside the material. Just like the work function, this is a fixed property of the semiconductor itself. Okay, so here is the single most important rule of the whole thing. When these two materials make physical contact, nature just demands that they find a balance, a state of equilibrium. And the only way for that to happen is for their Fermi levels, which you can kind of think of as the average energy of their electrons, sort of like a water level, to line up perfectly. So here's how that plays out. The electrons in the semiconductor are sitting at a higher energy level, so the second they touch, they just spill over into the lower energy metal. This flow of electrons leaves behind a bunch of positively charged atoms in the semiconductor, creating something we call a depletion region. All that positive charge actually starts to warp the energy landscape, causing the semiconductor's energy bands to bend upwards, building a hill, an energy barrier, right at that junction. And here's the really surprising part. We set out to make a simple connection, a wire. But what we actually built is a one-way street for electrons. They can easily flow from the semiconductor over to the metal, but that big energy hill we just built blocks them from coming back the other way. We've accidentally created a rectifier, a device that only lets current flow in one direction. This is known as a Schottky Diode. Now, that was the textbook version, in a perfect world. But as you know, the real world is never quite that clean. And it turns out, these real-world imperfections completely change how the junction behaves. See, our ideal model assumed a perfectly clean, flawless surface. But reality? Oh, it's a lot messier. At the surface of any real semiconductor, the perfect crystal structure is broken. You've got dangling atomic bonds, impurities, all kinds of defects. And all these imperfections, they create these tiny little electronic traps right at the surface called, well, surface states. Think of them as rogue energy levels that shouldn't be there, sitting right in the forbidden energy gap. And they just love to snatch up and trap any passing electrons. Now, there are so many of these charge traps that they basically take control of the whole situation at the interface. They effectively pin the Fermi level to a very specific energy. And that energy level is dictated by the messy surface itself, not by the metal we're trying to connect to it. And this is a huge deal if you're an engineer. Why? Because it means it almost doesn't matter what metal you use. The height of that energy barrier is now locked in, determined entirely by the semiconductor's own surface physics. We've just lost our main knob for designing the junction we want. So, if nature is so insistent on building this barrier, and a stubborn one at that, how on earth do we engineer our way around it? Well, the answer comes from a really clever trick that takes advantage of the weird world of quantum mechanics. This is the challenge, right? We don't always want a one-way diode. In fact, most of the time, we just need a simple, low-resistance, two-way connection. That's called an ohmic contact. So how do we defeat this natural barrier and build that electron superhighway we need? The solution is actually beautiful in its simplicity. Instead of trying to get rid of the barrier, we just change its shape. We bombard the surface layer of the semiconductor with a massive amount of extra atoms, a process we call heavy doping. This flood of new charge carriers makes that depletion region shrink like crazy, and as it shrinks, the energy barrier becomes incredibly, incredibly thin. We're talking just a few nanometers wide. And when barriers get this thin, the strange and wonderful rules of quantum mechanics take over. A phenomenon called quantum tunneling kicks in, and it lets particles, like our electrons, do something that just seems impossible. They can pass straight through an energy barrier that they don't actually have enough energy to climb over. So by making that barrier ridiculously thin, we've completely changed the game. The electrons don't even bother trying to climb the energy hill anymore. They just tunnel right through it, almost like it's not even there. And because they can tunnel both ways, we get current flowing freely in both directions. We've built our highway. So, at the end of the day, that simple metal-to-semiconductor junction has two totally different destinies. If you have a wide barrier, the electrons have to climb over it, and you get a one-way Schottky diode. But if you engineer an ultra-thin barrier, the electrons just tunnel right through, and you get a two-way ohmic contact. So let's just quickly recap the whole story. You touch a metal to a semiconductor, and nature automatically wants to build a barrier, a Schottky diode. In the real world, surface defects make that barrier stubborn and hard to control. So the clever engineering fix isn't to remove it, but to make it super thin using heavy doping. And that lets electrons do their quantum magic and simply tunnel right on through. And that's really what it all comes down to. Whether that tiny junction becomes a barrier or a highway, a diode or a simple wire, the entire fate of our electronics is decided by our ability to control a barrier that's only a few atoms thick. It's an absolutely incredible piece of engineering, and it's what makes all of our modern technology possible.